Isfahan, at least like virtually. And so what I'll be talking about is joint work with a lot of people. So I wrote all of my collaborators there. And I should also say this is very much in progress, so it's not written yet. And so this is coming from a workshop that was already a while ago, namely it was from Winard um, Free, so Women in Non-Commutative Algebra and Representation Theory. And this was already in 2022. And so we're still working on our project. And so as you can also see from like all these people and where they are, it's a kind of an optimization problem, like where can we find a time and even like where can we meet? But we have managed so far, and we have some very nice results. But yeah, as I say, it's still in progress. And so, what is this all about? So so first I'll tell you a little bit about the main object we are interested in, namely additive friezes. And I guess some of you already know like multiplicative friezes. So I'll recall like what this has to do with multiplicative friezes. And then in the last part, how we get to the associahedra. Okay, so that's the plan. Let's see how far I get. And yeah, please also always interrupt me if you have any questions. And so let me start with like additive friezes. So these were defined by Shepard in Shepard in 1976. And of course, so Shepard, this is the Shepard from the Shepard-Todd classification of complex reflection groups. Um, so, and I think he was like talking to Coxeter, and then probably he knew about friezes. And so, what is an additive frieze? So it's an array of numbers. So an array of numbers. And so the numbers, so it's always a question, what do I mean with numbers? I just say here there's like real numbers. You could take like basically you could take any entries in a ring. So actually you could also do groups here, but let's stick to R here. And it has like this frieze form as in the multiplicative case, but for people who know about multiplicative friezes, we start with a row of zeros and end with a row of zeros instead of the rows of ones. And these entries have to satisfy a rule. So these satisfy the frieze rule, or the additive frieze rule, I should always say. And so what is this additive frieze rule? So whenever I have a diamond A, D, E, C in the frieze, so whenever I have something like, so here you can see a diamond, then I have A plus D equals C plus B, whoops, changing, C plus B plus one, yes. And so you basically you just like replace all the multiplication of addition in the determinant. But here, yeah, this plus one might be a little bit arbitrary. Actually, you could take like any constant. And so you could also take zero, but any constant is fine. Um, but you will, I mean, yeah, we'll see later. That's why we take one. And then also, as for the multiplicative friezes, F is a non-negative integer frieze if all the entries are in integers, non-negative integers. So, but we allow zeros. And then n, so n, this is like the number of non-trivial rows, as we see here. This is the so-called width of the frieze. And so, so here are two examples below. So again, I do not write the rows of zeros because it's getting like, if you write a lot of these friezes, then like adding the rows of zeros doesn't actually give you something. So these are two examples for n equals 3. So of positive, of non-negative integer friezes. And you see here we have like zeros here, and then we can just complete it like for the multiplicative friezes. And here we have something that looks a bit different. And I also wrote down for n equals 2. So for n equals 2, we can actually quite easily, you can just like find out like what are the conditions the entries have to satisfy. And you see that there are only 7 non-negative integer friezes, and they are like here. And yeah, you also see like for people knowing about multiplicative friezes, you will be interested in like where are the zeros in your frieze. And here you see there is something weird happening. There's also friezes without any zeros at all. So that's already quite interesting. But so for Shepard's friezes, so maybe I should say that Shepard already like showed in his paper that these friezes are actually so f of width n is periodic in the horizontal direction. And so I mean, like I complete, like I go left and right, so I'm allowed to go like infinitely in both directions. And the period, so period n plus 1. So we see here, so for this here, n is 2, and I need 3 numbers in my first row. So if you like compute, for example, this entry, you'll find it's a 1. If you compute this entry, you'll find it's a 0. So you only need this n plus 1. And then you also see there's some kind of more symmetry. So you have these like 2 triangles, and then if you complete, you will always have this like triangles that are stacked on top of each other. And yeah, this period is actually something that is something known. So this is actually the Coxeter number of the reflection group, or the quiver AN. And then, so these are, I just want to like give you that you can also generalize this non-negative friezes to stable translation quivers. So we get into representation theory quite quickly. So you can generalize to acyclic quivers. Or, I mean, we will mostly be interested in linking quivers. And I'll denote them by Q. And so I think I've only seen this in the paper of Mouillet Chenou from 2015. So that's the survey paper. Where so how can you define an additive frieze for any acyclic quiver? So you take your quiver Q, and then you form the translation quiver ZQ. So this here is the translation quiver. And then you add, so what are the arrows in here? So the arrows in ZQ, they are of the form Ki to Kj for any arrow ij in Q1. So this Q is always consisting of vertices and arrows. So whenever I have an arrow in Q, then I add an arrow in this cave copy of Q. So it's the same. Plus you add extra arrows from Kj to K plus 1 I for any ij and Q1. So you add the opposite arrows. And so how does this look like? So it looks very familiar. So if you take Q to be an N quiver, so I'll take here the orientation, so 1, 2, 3, and so on up to N. And then I can draw the translation quiver in this form. So I'll draw here just for N equals 1, 2, 3, 4, 5. So this quiver. And so this would be like, K, for example, here K is 0, K is 1, K is -1. And then I'm adding extra arrows. These ones here, so I'm always adding arrows. Oops, I drew one arrow too much. That's not good. Okay. And so 1, 2, 3. I hope it should always be the same number of arrows, but I'm getting somehow smaller. Okay, so I hope so far so good. So this is the stable translation quiver. Then on this quiver, we always have a translation, namely the AR translation. So tau that goes from the vertices of the stable translation quiver back to the vertices of the stable translation quiver. That sends every point ki to k minus 1 I. So this is called the AR translation. And so in the picture, so this is your usual AR translation. So we have that also in here. And then, well, what is an additive frieze? This is just basically an additive function. So an additive frieze is on that Q is a function f that goes from the vertices of the quiver to your ring. So I said the entries in the frieze, I'll take them as R, so real numbers. So let's stick with the real numbers. And like instead of the like additive frieze rule, I'll add the additive mesh relations. So if I have here a diamond k minus 1j, then I have here k I here k j is the AR translation. So here we have t k I. So this is like what the picture looks locally, and the mesh relation tells me that I have f of k minus 1 I, so f of tau of k of I plus f of I k. Whoops, I switch again, k and I. K I. This is the sum of f k j, where we have an arrow alpha j to I in Q1, and the f k minus 1 j, an arrow alpha from I to j in Q1. And so this would be the additive one, and so I have to add +1. So this is my, so I get back the original frieze. And then one can actually show that f is periodic again in the horizontal direction if and only if Q is an ADE Dinking quiver. So this actually follows from additive functions. So if I take instead of 1 here, if I just leave out the 1, then I have an additive function on my translation quiver, and so you can show that an additive function is periodic if and only if you are on a dinking quiver. And that's why we are also like just looking at dinking quivers. And in particular, we mostly, so far, we have only looked at AN friezes. And so we are looking at Q as AN. And of course, you could go to other types. And but what are the actual? Why are we interested in that? So, what are the questions? So, the questions we have about this is the first one is always like, well, I mean, we put these non-integers, the non-negative integers, and then like the first question is always like, how many are there? So, how many non-negative integer additive, I should always say additive integer friezes. And yeah, are there finitely many? And is there like, yeah, how can we even enumerate them? Is there like a nice way to do that? And the second one is, well, can we find a representation theoretic interpretation? So representation theoretic interpretation. So this probably requires some explanation. Yeah, you are a representation theorist. So it's this is coming from the multiplicative friezes where we can actually connect these multiplicative friezes to cluster categories. And so I want to say a little bit about this, but before, any questions so far? Okay, nobody's complaining, so we'll go to the second chapter. So the things we actually want to like know for our additive friezes are like we should be parallel somehow what we know about multiplicative friezes. And so this is like a little bit on Conway-Coxeter friezes and cluster categories of type A, and then so I said from additive friezes to associahedra. So we already have here the associahedron. So it's already appearing here. And so yeah, where is this all coming from? So I'll just briefly recall this. So Coxeter invented in around 1960s so-called multiplicative friezes. So, and yeah, these are basically you change a little bit how this thing looks like. So instead of starting with a row of zeros, we start with a row of ones. Then we have again entries Mij, and then we go to M1n, and then we have ones. And again, it's like going infinite in both directions. And so the width is again n here. And so Coxeter was interested in these friezes that satisfy the multiplicative frieze rule. So we have the multiplicative frieze rule. So for each diamond A, D, B, C, you have that AD minus BC is equal to 1. And then you want also what Coxeter studied was that Mij is actually a positive integer. So now we are not allowing 0, but only positive integers. And so for these multiplicative friezes, it was also shown by Coxeter that the period is not n plus 2, but actually n plus 3. So width plus 3, so it's not the Coxeter number. And the big theorem is due to Conway and Coxeter that says, and this is from 1973, that says actually these multiplicative friezes, I'll call them M for multiplicative or F mult. So they showed that the set of multiplicative friezes, F mult with N, that this is in bijection to triangulated polygons with N plus 3 vertices. And so this is, I'm not sure how familiar you are with this, but this goes via the quiddity sequence. So for example, if you have a frieze here with 2, so this one here, so here we have 1, 1, 2, 2. And so if I have that frieze, then I can associate a triangulated polygon to it. So this is of width 2. So my polygon should have width n plus 2, 3 vertices, so 5 vertices. And so I associate, so each, I look at the first row. This is my quiddity row, and then each integer here is indicating how many triangles of my triangulation are incident to a vertex. So I number my vertices in the polygon 1 to 5, and then I say, okay, 1 is incident to 3 triangles, 2 is incident to 1, and so you can see it's precisely this triangulation. So here I have 3, 1, 2, 2, 1. So you can, so for each triangulation, you can find a frieze, and for each frieze, you can find a triangulation. And so this is a very nice result. And so this in particular tells you that we can easily enumerate the multiplicative friezes because we know how to enumerate triangulation, namely by the Catalan number. So the number of F mult with N is the N plus first Catalan number. And so I don't write, well, I can write it down. So it's 1 over N plus 2, 2N plus 2 over N, choose N plus 1. And so this is the sequence. So for N equals 2, you get 5. For N equals 3, you get 14. And then I think you get 42 and so on. So this is the number of friezes. Of multiplicative friezes, and then you can. So now we're still in geometry. Then you can relate these multiplicative friezes to cluster algebras, and so this was due to Calderon and Chapoton. So Calderon and Chapoton in 2006. You can see the entries of the frieze, the multiplicative frieze, as cluster variables. So I don't write them down, but if you know something about cluster algebras, you can see that the entries are precisely the cluster variables. So for n, the entries are the cluster variables of the cluster algebra of type AN. So this is the relation, and then you can. So this is the algebra, and finally you can relate a cluster category to it. So this is the last thing. So what cluster category of type? Have to be careful. Yeah, type AN. And so this is due to, I'll just write it, abbreviation BMRRT, so Buan, Marsh, Reinecke, Wright, and Todorov, and then also the geometric interpretation is Calderon, Chapoton, Schiffler. they're both from 2006. So you can associate the cluster category CAN to this, which is the bounded derived category of modules over the path algebra of the quiver AN. And then you mod out by power inverse shift. So just so I guess this is the thing most people here are familiar with, or at least have seen it sometimes. But just to give you an idea how this is related to the geometry, I like always to draw a little table. So you have, whoops, let's put this together. So you have the combinatorics on one side. Then you have the, I'll put the frieze. Then you have the cluster algebra. So I'm not saying too much. And finally, you have the cluster category. So in the combinatorics, we have seen the n plus free gun corresponds to a Conway-Coxeter frieze. So this is the Conway-Coxeter frieze of width n. And so there's the triangulation. And then for the cluster algebra, we have a cluster algebra of type AN. So I'm not defining what a cluster algebra is here because we won't really need it. But then on the cluster category side, we have this CAN plus free. So I just, no, it's CAN. So I'm correct here. So it's CAN. And so in this category, well, your objects are the indecomposable modules over the path algebra, plus you get some extra ones, the shifted projectives. So I'll do an example later. Then we have in the combinatorial picture, we have the arcs. So these are just from I to J. So if I have here my polygon and then have an arc from I to J, they correspond to so if I have my triangulated polygon, then I'll take an arc in the triangulation, and this corresponds to a 1 in a multiplicative frieze. And this corresponds to the cluster variables. So so x1 up to xn. So we have exactly n of them. And this corresponds to the indecomposable modules and KAM mod. And then we have the shifts of the projectives. So these are the objects here. And then the triangulation. So I think, yeah. So wait, I did make a mistake. So these are not the ones in the frieze, these are the entries in the frieze, sorry. So every entry in the frieze corresponds to a cluster variable in x1 to xn. Then the triangulation corresponds to a maximal collection of ones in the frieze, and this now is like a cluster, which I don't define. And this corresponds to a cluster tilting object in the category. And then I can do here the flip of a diagonal. This corresponds here. We have some mutation, so you can look up how that works. We did that in joint work with Karin and Gordana Todorov and Sira Gratz and Kristina Zerienko. Then here we have the cluster algebra mutation. And here on the cluster category side, we have an this add t mod, yeah, j. So I'm just writing it. I'm not really saying too much about mutation. So just that we see these are the like important things we can do with triangulations of polygons and with friezes, with multiplicative friezes. And so for our problem is like kind of we want to do the same. We want to see somehow similar object, and well, object is a bad name, similar facts for this additive friezes. So can we find somehow also a kind of a cluster category for an additive frieze? Can mutate additive friezes and so on? And so just to give you one example for the quiver, and also because I need it for associahedron, I'll draw you CA2, so the cluster category for the quiver cube of type A2. So I just have two vertices. Then the cluster category looks like, so I'm drawing the modules in the category. So this would be my, so this here is mod A, mod, or K2 mod, and then the shifts of the projectives. So this is 2, 1 and 1, 2 shift. And then the cluster category just continues periodically, 1, 2. And here we have, I'm always getting confused. Which one is the next one? 1. And then here we have 2 shift and 1, 2 shift, and so on. So this continues in both directions. I don't draw the arrows because they're a little bit confusing. And then we get the frieze from this via the so-called Caldereau-Chaponton map that associates each object in the cluster category a number. And so we get here exactly the frieze of 3, 2, 3, 2, 1, 1, 3, 2, 3, and so on. So without the ones. And so this is this is an example how to get from the quiver to the frieze. And so one thing I will actually need is like that this frieze here has like a fundamental domain. This thing here, so probably I should copy this. Okay, so this is about multiplicative friezes. So then for these multiplicative friezes, we can actually, or for like cluster categories of type A, we can associate a polytope as well. So this is actually coming from physics. So further, get an associahedron from so this is like the explicit construction from physics. So it's inspired. So I should say it's inspired from physics, namely by a paper of Arkani Hamid and Bai, He, and Yan. So these are all physicists, and so they were kind of looking at so-called scattering amplitudes, and somehow this was then translated to representation theory in a nice paper by Mat. Wait, oh my guess. Mat. Chapelier, Laguet, Touville, Moussaband. That's too many names. I think that's everybody. Yeah, Thomas and Yildirim. So, 2018. And then there's also like a more general version that came a little bit later. This is due to Padrol, Paru, Pilot, and Clamodon. And so this is, I think, was on the archive roughly a little bit later, but was published in 2023. And this was actually published in 2024. It was published later, but was actually earlier on the archive. And so they construct a polytope from a thinking quiver in the following way. So the construction, so you take your quiver. So this is the thinking quiver Q 01. So this is of thinking type. And so I will always look at AN only, but so you could do this for any thinking quiver. And so N is the number of vertices of the quiver, and then capital N is the number of indecomposable KQ modules, and then also CQ. This is the cluster category, so this is DBKQ mod modulo tau inverse and shift. And then you also can take C to be any tuple of integers, and you take one for each of the indecomposable objects. So one, so this is important. So one for each indecomposable KQ module. So you have the shift of the projectives as well, but you only take like the indecomposable KQ modules here. And so this is a tuple of integers. So this will be the ones for us. And from this, you look then at the space EC. So this is the now tuple of real numbers, where now we look at all the objects, indecomposable objects in the cluster category, so also the shift of the projectives, such that a certain equation is satisfied, namely xm plus xl is equal to xk plus cm whenever we have a AR triangle of the form m goes to k, goes to L, goes to M, shift in CQ. And so here, an important M is, so this here, I only look at AR triangles that start at a module. So this is actually something that is in the composable of KQ mod. And so I look at this set. So this is a set that is like defined by linear equations, one for each AR sequence. So this will be like in general infinite, but then you can intersect this with the positive orthant. So you can intersect EC with R n plus n greater or equal 0. So n plus n, this is the number of indecomposable objects in your cluster category. And so you will get something that is what's called a polytope. So it's bounded. And so this is living in a very high dimensional space in general, but you can project it down to Rn. So you get a projection pi from EC to Rn. And so EC, so that lives like, so you have the space is like all, is the dimension of the space is like all indecomposable objects in your cluster category, many, and you project down onto the tuple of integers that corresponds to the shift of the projectives. So you only get down to n. And so then you have something, so you project something finite onto something polytope in Rn, and this thing is called AC. So this is precisely the projection of UC in Rn, and this thing. So this is the theorem of all these people. So I just write down the abbreviations. So it is BCD NTY. They say that A1. So I'm just interested when all the constants are equal to 1. This is a generalized associahedron. And whose normal fan is the G vector fan. Of the cluster algebra. AQ. With respect, so I should say the complete thing with respect to the seed corresponding to the cluster tilt is a cluster tilting object, the sum of the projectives. So this is the correct thing. So basically, I have chosen my cluster, and then the shift of the projective is the extra modules I get, and I project on them, and this gives me the associahedron. And so for our example of A2, what do we get here? So for quiver A2, so not sure if that still exists here. Yes, it does still exist here. So this is the quiver. And so the recipe says like you have to associate to each of the entries in the module category. We get an equation. So we give them B, C, D, E. So we have 5 objects in the cluster category. And then the relations, I only get 3 relations because I have only 3 objects in the module category. And the relations are A plus C equals B plus 1. Then B plus D equals C plus 1. And C plus E equals D plus 1. So these are the relations I get. And then from the construction, we also have to take that everything is positive. So plus entries greater or equal to 0. So we get inequalities. And so if we compute the possible inequalities and only take non-negative integers, so you get 8 so you get 8 solutions with integers, and so you actually, so I write down the vector of that corresponds to the shift of the projectives, and then you can find out the other values. So I get 1, 2, 0, 1, 2, 2, 0, 0, and these are the 0, 0, 2, 1, and I made a mistake here. So it's 0, 0, 2, 0, 2, 1, 1, 0, and 1, 1. So these are all the solutions. And then the polytope they define looks as follows. So this is the convex hull of all these things. And so it's here, 2, 1, 2. And so all the points in here. And so you see you have 5 vertices that corresponds to the cluster tilting objects, and the rest is just the integer points. Okay, and so, oops, I don't have too much time left. But so we see somehow this looks like additive friezes, but it's not quite additive friezes, because what you see is if you take this guy here, so if you take the 2, 0, write down what would the frieze look like. So the numbers here, they look as follows. So 2, 3, 2, 0. So this is the size I'm projecting on. Then here, everything is like non-negative integers. But then if I compute the next number here, so 2 minus 1 equals 0 plus 1. So my next entry here is actually not a positive integer. So this is like, so we get some kind of additive friezes, but there are somehow too many of them. So this is not modeling precisely the additive friezes, and so this is now where we come in. So now this is what's currently in our write-up called our category. So probably this will get another name eventually. And our polytope also this eventually should get another name. So now we try to just mimic the construction of this like cluster category going to the associahedron. Namely, instead of the cluster category, we wanted to take a category that has the same periodicity properties. So the idea is instead of CQ, we take the so-called root category, RQ. So this is, so again, we take a dbkq mod. So the construction should work for any thinking quiver, but instead of modding out by tau inverse shift, you just mod out by the square of the shift. So these categories, these have actually been studied, not as much as the cluster category, but people are aware of them. So they were studied, for example, by Happel. That was the first one, probably in 87. And then it was shown that these categories are triangulated. You can see this from a paper of Peng and Xiao from, I didn't write down the year, but it was somewhere in the 2000s. And you can even find a geometric model that is due to Bauer and Marsh. So, which is with oriented diagonals. And so this category, the shape of the AR quiver is correct for the additive friezes. So the shape, so now I'm talking only about Q is AN. So the shape of the AR quiver is correct because, well, we will have so this here is mod AN, and then here we will have the shift of mod AN, and then it will continue with mod AN. So it has the right periodicity. And so I'll be done in like 3 minutes. I just want to write down the definition of the polytope and what we know so far about it. And so then we can also get the polytope. So this is now our polytope. So we modify the definition of PPP or the other ones. So we can look at a tuple, so constant tuple. So again, we will only use, so this will be always 1 for us. And then the number, so the number of indecomposable is 2n. Then we can define, similar as before, we can define FD. So this is now the set of so these are the O in R tuple for every indecomposable in this root category RQ. So I'm assuming ym is in R. And the equation is exactly the Frieze relation. So for each AR triangle, we have ym plus yl equals yk plus dm for all AR triangles m to k to l, and then 1 in RQ. So we want to have this satisfied for all the, so this dm is always 1 for all the modules in the category. And so this is something that lives in R2n. And then again, we can define the intersection with the positive orthant. So VD is FD intersected with R greater equals 0 R2n. So all the positive or non-negative solutions. And then you can also define the same projection R2n to Rn, where we just project this tuple ym onto the slice where we have the shifted projectives. So yp and shift. And we can define finally our polytope. So this is just a projection of VD, and we call it B1. So 1 is always the or VD. So we always take D equals a constant 1. So if we do that, yeah, so I had the picture of the associahedron up here. So let me just copy this. Oops. And I just want here. And we will lose this 2 0 points. So our polytope, I'll draw it in yellow, whoops, will look like this. So we get some kind of symmetrization. So this is B1 in our example. And so we get some kind of symmetrization. And so this is now a proposition. So first of all, so V. So first of all, we can show that this B1 is a full dimensional polytope. Then it is it doesn't have any irredundant inequalities defining it. So these inequalities are all the correct ones. The facets correspond to the entries of the additive frieze. And this is also like, it's actually a polytope, so it's bounded. So this is all what we expect. Then we can also, so we can interpret so you get some kind of homological interpretation. So I'm not saying, since I'm pretty much out of time, I'm sorry. So we get an homological interpretation of the entry of entries as Hom spaces. But currently this is like only working if we take slices, and so not for all the friezes. So only some of them are like coming from some homological thing. And then the interesting thing for people studying polytopes is that we can also characterize how our polytope is related to the actual associahedron, namely the vertices of B1 are the projection of friezes. So where this is an additive integer frieze, so non-negative integer frieze, with a maximal number of zeros. And so there are at least n zeros, but we can have more. And so this is very different to the so these are not cluster tilting objects, unfortunately. Then finally, so this is the last thing I want to say is that so if we look at the so-called the map sigma from Rn to Rn, that just like sends each point in Rn to the point where I just reorder the variables, then this gives me a characterization of our B of our B1, namely these are like all the points in the associahedron from coming from the cluster category, such that sigma of A is contained again in A1. And so somehow our polytope is a symmetrization of the associahedron, which you can see in the picture here. So the associahedron is this one here. And so we see if we like change coordinates at this point, we would land here. So it's not contained in the associahedron. And so our polytope is in some sense the symmetrization. And yeah, sorry, I'm over time, but maybe I should say like we're still one thing we still don't really understand is what are the vertices of the polytope. So like, can we somehow characterize them homologically? So it's not cluster tilting objects in the root category, unfortunately, but we're still working on this. And yeah, this is all I have time to say.
So thank you very much for your very nice talk. Thank you. Are there any questions or comments? So maybe I start with some small question. What about the interpretation of the mutation in this?
A very good question. So that's yeah, we don't know. So this is actually something that's completely open. So we don't. So one thing is that is not quite clear. Can we always mutate? So for mutation, you would want like you can mutate in each direction somehow. And so one thing that is not quite clear is if the associahedron that so our polytope, if that's what the polytope people call a simple polytope. So if each vertex has exactly n edges coming out of it. And so like last week I was at this conference in Lumini with the polytope people, and they said like, oh yeah, our polytope should be some intersection of associahedron, and then it will be a simple polytope. So it's probably okay. So you should be able to mutate in each direction. But yeah, how this works is a whole different question. And yeah, we can do this in the category. So it's yeah.
And other question, what about the infinite additive frieze?
Oh, yeah, also a very good question. We haven't thought about this at all. So yeah, I mean, I don't know. So I also like it would be like an additive function on an infinite quiver, but yeah.
So any other question or comments? Yes, Karin, please.
So you define this B or like also their A with an arbitrary vector D. So what happens if you change the vector D?
That's a question that I think would be interesting, but so far, so what you would so if you vary the values, then somehow at some point your polytope will degenerate. So that means basically you slide the defining inequalities, and for example, if in this so if in the associahedron, so you would basically take this thing and then you would like slide it in each direction, and so you see like if you go too low, then somehow you won't get any solutions, any positive solutions, and so yeah, it's kind of like this would be a deformation of the polytope. But yeah, I'm not so yeah, you should get some deformations, but yeah, I don't really know what the differences are.
So thank you. Oh, any other question or comments? So if not the case, thank you speaker again. Thank you very much.
Thank you very much. Okay.